Welcome back after the lunch break. So it's my pleasure to introduce the first speaker, Julian Gonzales, who's going to talk about Hausdorff covers for non-Hausdorff.
Thank you very much for the organising this event, and also particular thanks to Ian Fenn for giving the opportunity to speak. So I'm talking about this recent joint project with Kevin Bricks, Jeremy Hume, and my supervisor Shin Lee, where we look at a Hausdorff cover for non-Hausdorff cover. So first, a bit of background. Throughout, G has been a tile groupoid, locally compact, Hausdorff unit state. This is an assumption throughout. For now, assuming G is Hausdorff. This is an assumption just for this slide. And so somehow it's been a bit of a theme. We start with properties of some dynamical object, the groupoid. We look at properties of its corresponding C-star algebra and try and build a dictionary. Two adjectives I'm interested in today, nuclearity and simplicity of the C-star algebra. In the Hausdorff case, we have some good answers. So the C-star algebra is nuclear, if and only if the groupoids are amenable. As for simplicity, so maybe the corresponding ideas we should think of are minimal and effective. So this is maybe a slight lie, but under certain conditions, these are equivalent. Okay, so this is the Hausdorff case, but what now happens if G isn't Hausdorff? You're working with something non-Hausdorff, lots of technical difficulties arise. So maybe another question is, can we reduce problems for non-Hausdorff groupoids to the Hausdorff case? So my talk's roughly in two halves. The first half, I'll address this problem directly using this so-called Hausdorff cover. And then the second half, I look at this so-called singular idea and try and describe some of the progress we've made towards understanding it using the Hausdorff cover. Okay. Possibly I'll talk about my examples first. So if you try and picture how non-Hausdorff groupoids, you might seem like a very strange thing to try and think about. This is maybe the easiest example we can think of. So you just take, here I just have the unit interval. First at the point 1, I have two separate points. What does this mean? So let's say this red point, an open neighborhood is U1. So this is just another copy of unit interval. The blue point similarly has such an open neighborhood. This space you can tell already is non-Hausdorff. What's its groupoid structure? Here I just take trivial multiplication, so all the way from 0 to the open interval up to 1. The 2 points here, I just take Z02 here. So the multiplication's very easy, and you can believe me that this is an tile groupoid. The second example is maybe a bit more complicated. I'm not sure how visible the different colors are. But first of all, we start with this space. So just imagine 3 copies of the unit interval glued together at a point. This is going to be my unit space. Then imagine this picture sort of in 3D. So down here, I have another copy of this space. Just again, 3 unit intervals somehow meeting at a point here. However, in the middle, something strange is happening. I somehow have 4 points. So here, this black one, and also a red, a blue, and a green dot. What's my topology looking like? So my original black shape, this is an open set. It's going to be an open bisection. And then I have 4 other open bisections. I call them, there's 3 others. There's U1, U2, U3, and U4. This red one, again, is just another copy of the original shape. But I write it here close to this black one because somehow we're glued together. So, so U2 is an open set, but it's equal, so it sort of lines up with this, the original black one there. And importantly, it contains this red point here, so it somehow lives in the middle. Similarly for the green ones and the blue ones. So this is a non-Hausdorff space. Well, what's my multiplication? On the outside, I just take Z02Z. In the center, I have the Klein 4 group. Again, this is a non-Hausdorff groupoid. Maybe you don't believe me, but again, this is. Right. So some quick recap on C-star algebras. So hopefully, well, you're aware of the construction in the Hausdorff case. I'll try and describe the main difference for non-Hausdorff groupoids. So in the Hausdorff case, the C-star algebras are just defined as completions of CC of G, so compactly supported continuous functions. In the non-Hausdorff setting, these aren't the right functions to look at. There sort of aren't enough continuous functions. In particular, they don't separate points. So instead, we look at this algebra that I call Kelly C. And it's the span of functions on the groupoid of the complex numbers, which somehow live in CC of U or use an open bisection. Because of the structure of my groupoid, any open bisection is locally compact in Hausdorff, and so this is a nice place to look at. What I really mean here is that when I write that F's in CC of U, again, I can use the pointer. Okay. The restriction of F to U is in CC of U, and F0 everywhere else. So I build this Kelly C algebra by taking the span of all such functions. Now, importantly, this algebra Kelly C, these functions aren't continuous. And this is one of the main difficulties which arises when looking at non-Hausdorff groupoids. Okay, and the C-star algebra is defined as the reduced C-star algebra, which we're looking at today, is defined as a completion of CC, Kelly C of G, in exactly the same way as it is for the Hausdorff case. And something we'll use here is because G is a tile, elements of the reduced C-star algebra can still be viewed as functions on the groupoid. Okay, so this is all the background I'm giving, but what's important here is the C-star algebra is built from Kelly C algebra, and this is the only real difference compared to the Hausdorff case. So here's the main object, the main tool we'll be using today, the so-called Hausdorff cover groupoid. So here CG denotes the space of all closed subsets of G, and I can include G into this space just by sending G to singletons. The Hausdorff cover is then the closure of this with respect to the Feld topology. I want to find the Feld topology, but we really can understand these closed subsets. This isn't some very abstract thing. We can, picture what this Hausdorff cover looks like. And naturally, you can give this Hausdorff cover the structure of a Hausdorff italic groupoid. Yes, and this Feld topology allows us to explicitly describe elements of the Hausdorff cover. So I gave 2 examples earlier. I've also drawn what that Hausdorff cover looks like. So in the first case, where we had the interval with 2 points of 1, the Hausdorff cover is again an interval, but now I've closed it up here, and the 2 points have sort of been separated and sent far away. So now, okay, they're 2 discrete points, isolated points. So now I have a Hausdorff object. It's again the tile groupoid. In this case, something similar happens. So you have this shape meeting at the center with 3 points. This sort of gets split up so that you have 3 copies of the unit interval. Same on the second level above. And the 4 points that somehow lived in the center and caused the non-Hausdorffness, they get moved far away and become discrete points. Right, so briefly some properties of the Hausdorff cover. So functions in this Kelly C algebra which weren't continuous actually genuinely do extend to continuous functions on the Hausdorff cover. So whereas they were badly behaved on the original groupoid G, we can now view them as genuinely continuous functions on the cover. This then extends to isometric embeddings of the C-star algebras. So firstly, the reduced, and then also the full C-star algebra. And this then brings us on to the first theorem. So assume G is sigma compact. The Hausdorff cover allows us to understand amenability. So the original groupoid is amenable if and only if the Hausdorff cover is amenable. And then this is equivalent to nuclearity of all the associated C-star algebras. So this sort of completely answers the question of amenability for non-Hausdorff groupoids by reducing it to the Hausdorff case. Okay. Now, in order to motivate the study of this singular ideal, I'm looking at the second adjective of C-star algebras, so simplicity. I think we can't quite see the top, but what's important is that the singular ideal J, well, it's an ideal of the C-star algebra, so it's clearly going to be an obstruction to simplicity. However, we actually understand simplicity of the C-star algebra modulo J. So I'll reference two results. First, this 5-author paper, including Lisa and Hayden, 3 others. If you assume the singular ideal vanishes, then simplicity of the C-star algebra is equivalent to minimality and effectiveness of the groupoid. If you assume again also that G is amenable and second countable. But if you quite literally just mod out by this J, then the resulting quotient C-star algebra, the simplicity is characterized in this 5-author paper, including Shin and Matthew Kennedy. Right. So we understand simplicity. Oh, sorry, there's one more theorem to mention. So we've also contributed to this now using this Hausdorff cover groupoid. So if we assume that G is covered by counter-remaining bisections, then there exists some closed invariant subgroupoid of this Hausdorff cover. I want to find what this is, but what's important is it's still a Hausdorff et al. Groupoid, and it satisfies the following property. So this quotient C-star algebra, its minimality is equivalent to minimality of the reduced C-star algebra of this new groupoid. So if you want to understand simplicity of this quotient, somehow this question, oh sorry, this is meant to say simple, not minimal. Okay, but anyway, simplicity of this C-star algebra is again sort of reduced to the case of Hausdorff groupoids. And in fact, this allows us to recover the 2 previous results. Okay. We still have the problem of this singular ideal. So what do we understand about this? Sorry, I haven't actually defined it yet, but here's the definition. So given the function f, I write this sup O for its strict support suggests a set of non-zero elements. And the singular ideal is a set of functions in the C-star algebra for which this strict support has empty interior. Now, this is sort of a quite strange property to think about. If you're used to working with continuous functions, then clearly its strict support should never have empty interior. It should be an open set. If there's empty interior, then your function is just 0. But this is possible in the case of non-Hausdorff groupoids. So an example could be the following here. So I can take the indicator at this first bisection U1 and then subtract the indicator at the second bisection U2. And this is just equal to the indicator of my 2 points here. Maybe I'll write indicator here. So this is a function that's zero along this whole open interval and only non-zero on these 2 points. Therefore, it has strict support as empty interior. Okay. In order to understand simplicity, we want to see when this thing vanishes, so when it's 0. And here are a couple of results in this direction. So Neshviev and Schwartz in 2023 give some sufficient conditions for vanishing. And then in the case of groupoids arising from contracting self-similar groups, this 4-author paper from this year give a characterization following work of Nora and Ben Steinberg in 2023. And then here's our contribution. So let G be an étale groupoid. This theorem doesn't quite characterize J. What it does, it characterizes the intersection of J with this dense subalgebra of the C-star algebra. Now it's quite a long theorem, and the conditions probably look a bit technical. If I have time, I can try and explain it in terms of these two examples. So this intersection is non-zero if and only if there exists a finite collection of bisections satisfying three conditions. So they all have the same source. If you take one and remove the others, you're left with a non-empty set with empty interior, and then some complicated condition here, which I won't talk about. But in the sort of context of, okay, we could call this conditions S0. But in the context of Neschiev and Schwartz's paper, these first two conditions are quite similar to the necessary condition they gave there. And so somehow when you add this third condition, it becomes sufficient. Okay. I wrote this I here to sort of prepare for this. You can just check immediately that if you take this open bisection U1 and this open bisection U2, then you satisfy all three conditions. The set you have here has one element, so you clearly can't span the whole of C2. And it's fairly constructive in that if you then apply this result, then you build the singular function that I described before. Now, if we look at this groupoid, if you want to satisfy the first two conditions, you're more or less forced to choose the four bisections U1, U2, U3, and U4 that I mentioned earlier. You clearly don't have the same source. And then if you take one and remove everything else, you're left with one of these middle points. You satisfy the second condition. However, the third one, you have sort of six things in this set. And when you take the span, there's not enough cancellation, or in some sense, there's too much cancellation. So you fail to satisfy the third condition. And this sort of tells you that the singular ideal in this groupoid actually vanishes. If you're familiar with the language of Neschiev and Schwartz, this is an example of a groupoid with an extremely dangerous point, but for which the singular ideal vanishes. Okay. So this is a characterization for when J intersect curly C vanishes. What we really want to understand is when J vanishes, if we're interested in the C-star algebraic setting. And so we look for a condition which ensures the equivalence of these two conditions. And what we do is put a constraint on how large the closure of the unit space is. And this gives us the following theorem. So if we assume that the closure of the unit space is finite on all fibers, then these two conditions are equivalent. Therefore, for groupoids satisfying this condition, we have a characterization for when the singular ideal vanishes in terms of the condition S0 we saw on the previous slide. Groupoids arising from contracting self-similar groups satisfy this condition on how large the closure of the unit space is. So in particular, this generalizes the results from the earlier paper this year. Okay. Maybe I have a minute or two. We also have results in the setting of Steinberg algebras. I'll briefly go through this. So in the setting of Steinberg algebras, you look at groupoids which are ample. So this is a groupoid which has a basis of compact open bisections. And if you're given a ring, you define the associated Steinberg algebra to be the span of functions like this. So here I use an indicator function, the function from the groupoid to the ring, and it takes the constant value R on this compact open bisection U, and it's zero everywhere else. If you take functions of this form and just take their span. And you define the singular ideal in the same way. So it's a set of functions in the Steinberg algebra for which the strict support is empty interior. Now, again, people are interested in vanishing conditions for this Steinberg algebra. So, for example, Nora and Ben Steinberg, they characterize when this quotient algebra is simple, given a field K. So this quotient is simple if and only if the groupoid is minimal and topologically free. Then if you want to know when J vanishes, these two papers give you results in the setting of groupoids arising from contracting self-similar groups. So this is again the paper I mentioned earlier this year. This is another work from Nora and Ben in 2023. But what we saw earlier was a characterization of when this J intersect curly C vanished. And this is an algebraic result. So somehow you might hope that the methods from that proof could apply to this algebraic setting of Steinberg algebras. Indeed they do. So okay, there'll be a big theorem, technical theorem on the next slide that doesn't really matter. But the point is, you can completely characterize vanishing of the singular ideal in Steinberg algebras using the groupoid properties. So here's the big theorem. And I write this red line here because there are no longer any conditions on the groupoid. Okay, then finally the final point is to mention that this vanishing condition only actually depends on the orders of elements in R. So we somehow also recover previous results, which say that if R is a field, all you need to check is its characteristic. Okay, that's all I have to say. First.
Any questions for Julian? Yes.
So back early on, you were mentioning that you have really nice embeddings of the C-star algebra for your non-Hausdorff groupoids into the Hausdorff covers. Are these like particularly nice embeddings? Is that how you get the amenability results?
So there's still sort of work to do to actually get here. So this one, in order to get the amenability results, you need to extend representations from this from the original groupoid to the Hausdorff cover groupoid. And that somehow lets you extend representations to get the full C-star algebra. This is using a method of Diego Martinez and I'll say these was. Other than that, I mean, the approach is a bit ad hoc. I don't know that there's much you can say about them being particularly nice, but I don't know. Maybe there's more to look into. Right. Okay.
Kind of building on that, like, so you're saying like, so I guess if I understand the Against paper correctly, like they kind of prove this sort of like a new theory kind of thing, but just without making it a Hausdorff problem, right? Essentially, like, isn't it like a non-Hausdorff amenability thing, right? And then you sort of make the problem a Hausdorff. You turn it in, you convert it to like a Hausdorff version, and then you use the Hausdorff result. But that's what you're saying, right? Is that
The way that we prove
Yeah,
it,
yeah.
yes, more or less.
But then you still have to use Diego's stuff anyway.
So we don't have to apply their theorems. We just sort of modify one of their methods.
Oh, that's what I meant by Diego's stuff. I didn't mean you literally use his theorem.
Oh, yes.
So I don't know how to word what I'm trying to say. I'm trying to say, like, do you think that there's any value in proving things just without using your methods, or do you think your methods make everything nicer? Just tackling any like non-Hausdorff problem, do you think that people should kind of Hausdorffify as much as possible and then?
I think it meant that this proof wasn't too complicated. So essentially you prove amenability of the two groupoids are equivalent. This is fairly easy. And then you prove that nuclearity of these two C-star algebras is equivalent. And then using the Hausdorff results, you're more or less done. Just maybe check some other conditions. And there's also a similar idea when you get here. So you have that these two minimality, the simplicity of these two C-star algebras is equivalent. This is a Hausdorff groupoid, so somehow you might understand its simplicity better. Then you go back to the groupoids and you check that minimality and topological freeness and stuff is equivalent. And then you can recover simplicity results for non-Hausdorff groupoids just using the Hausdorff results. So I think you can just avoid lots of technical difficulties using this approach. And that's, yeah, maybe the main upshot.
Great. Any last questions for Julian? If not, let us thank you again.